All right, guys, so my goal today is show you how to do a little bit of stuff with uncertainties, specifically uncertainties of slopes or gradients. And I also want to show you how to do linearization and teach you the principle behind that. So I'm going to show you one example, and then you'll be able to work through a couple more in your homework. Okay, so looking at this, you can see that our steps are going to be, we're going to graph the data, we're going to identify the function type, we're going to draw error bars, we're going to calculate the percentage uncertainty for the first and last point. We're going to linearize the data by changing x or y axis. We're going to draw the maximum and minimum gradient lines, and we're going to calculate the uncertainty in the gradient. All right? And it's going to be fun. Yeah. That I have already plotted the points and drawn on the error bars. Now, for this specific activity, we're going to focus on vertical error bars. We're going to assume that the x value was able to be measured accurately enough that the error bars are very, very small. Okay, so we've got our data here, we've got the graph put up, we've got the error bars. Now, that's step one. Step two is to identify the function type. Okay, now you look at this, and really there's only a couple of options. When we're identifying the function type, we want to try to identify something that's the simplest possible function. Okay, so with this one, we do see if I were to draw a line of best fit, it would be some type of curve like this, right? That would go like that. It could possibly be exponential. Okay. Could be exponential, though it doesn't seem like it gets quite steep enough for an exponential graph. The other option really is quadratic. Okay, there are other possibilities, but given that it's centered here at 0, 0, then I'm going to make the assumption that it's probably one of these, that it's not, say, a inverse reciprocal graph that's been shifted to the right or the left or whatnot. So we're going to assume one of these two. Now, honestly, given the situation, a ball rolling down a ramp, that should be governed by kinematics. And we know that in kinematics, the position is related to gravity times time squared. And so it should be a time squared thing. It should be a quadratic relationship. But I'm going to go ahead and work through both of these so that you can see what it would look like if we do something that maybe doesn't quite fit the right way. All right? So the first thing we're going to do is we just identified, we're pretty sure that it's quadratic, and we've already drawn the error bars, so we're moving along in our procedure here. So now we want to calculate the percentage uncertainty for the first and last point on the graph. Okay, so to get the percentage uncertainty, remember that percentage uncertainty is just the uncertainty divided by the value itself. Okay, so for this last point, the uncertainty is 2 centimeters, and the value is 58. So 2 over 58. And if I pull out my calculator and go 2 divided by 58, and I'm going to do the equivalent, I get 0.034. And it looks like I've got 2 sig figs everywhere here, so I'm going to stick with that. So 0.034 for the last point. Okay, now I'm going to look at the first point. Okay, now the first point here is 1, 3. Now, it's probably pretty safe to assume that it goes through 0, 0 down here, but that's not something that we know for certain. It's not technically on here, so we're going to go ahead and go with what we got. Our first point will be 1, 3. So again, the uncertainty is still plus or minus 2 centimeters, and so 2 divided by the actual value, which was 3, which if it's only 3 centimeters away, plus or minus 2 centimeters is actually a really big deal, right? And so in this case, I get 0.67, which is the first point, okay? So you can see in this situation that the fractional or the percentage uncertainty is not consistent, right? It changes. The further points have a lower percentage uncertainty than the initial points do. And that's fine. We also notice that the absolute uncertainty is the same. So be aware of the situation. Sometimes it will tell us that the absolute uncertainty is the same, and sometimes it will tell us that the percentage uncertainty is the same. So just know what the question is asking for and what the situation is so that you can understand what you're supposed to be doing. Now, the next step is the biggie. We're going to linearize the data by changing the x or y axis appropriately. Okay, so here's the theory behind this. The theory is if this is really a quadratic, okay, then it would be, you could write it as an equation, y equals ax squared. Now notice I don't have the bx plus c. That's because it's going through apparently 0, 0. So I don't need the linear term or the constant term in my quadratic because those are the things that cause it to move around. So it would be y equals ax squared. What if on the x-axis, instead of graphing x, I graph x squared? So I put the values of x squared there. Let me show you what I mean. So we're going to move this up. We're going to create a new graph down here. Okay, I'm going to create a new table, okay, for x squared versus y. Okay, so x squared, the original times were 1, 2, 3, 4, 5, and 6. So x squared would be 1, 2 squared would be 4, 3 squared would be 9, 16, 25, and 36, right? So those are just the squares of the times that I originally had, okay? Now y, I'm going to leave exactly the same way. So I'm just going to copy those down from my table. So 3, 7, 17, 28, 41, 58. Now watch what happens when I graph this new thing. So on the x-axis I now have x squared, and on the y-axis I now have y. Now if this is really quadratic, what do I expect? X squared is now x. So what would I get if I graphed y equals ax? Well, I should get a linear graph. That's why this is called linearization. So if this is really quadratic, if x really has that quadratic relationship, then this should linearize my graph. So I need x to go up to 36, 5, 10, 15, 20, 25, 30, 35, 40. So it looks like I can go by ones there. I need y to go up to 58, which doesn't look like it's going to happen. So maybe I go by threes, 3, 6, 9, and then this would be 18, and then 27, and then 36. Oh, I'm going to run out of space, but that's okay. 45, 54. That last point, I'll just put a little bit higher. That should be all right. So I've got my y values here. So my first point I'm going to put at 1, 3, which will be right here. I'm going by ones down here. Okay, 5, 10, 15, 20, 25, 30, 35. Okay, then I'm going to go to 4, 7. So 4, 7, which will be somewhere around here. Then I'll go to 9, 17. 9, 17, somewhere around there. 16, 28. 16, 27, 28. Each one of those is 3. 25, 41, 25, 41, so that would be 42, so 41, about right there. And then 36, 58, which would be just off the graph here, somewhere up there. All right, now you'll notice that my new line is very nearly linear. It's not perfect, okay, but it's very nearly linear. Okay, now, one thing that I want to make sure to do here is I want to make sure that I have my uncertainty. Okay, so remember my uncertainty before was plus or minus 2 centimeters. Okay, I have squared the x values. I have not squared the y values. So that means that the y values are going to just stay the way that they are. That might affect the uncertainty in x. It doesn't affect the uncertainty in y. So my uncertainty in y is still plus or minus 2 centimeters. So I'm going to try to do that 2 centimeters here. Okay, 2 centimeters up, 2 centimeters down, 2 centimeters up, 2 centimeters down, 2 up, 2 down, 2 up, 2 down, and then 2 up, 2 down, more or less. Okay? Now with that, we should be able to draw a line of best fit. You can see if I bring my ruler in here, I can draw a fairly nice line that could be going down there. Now I'm not going to draw it yet because we still have a couple other things that we need to do, but you can see that my points are now more or less linear. Okay, so I'm going to go ahead and finish this process, and then I'm going to show you what would happen if we chose the incorrect model, if we chose exponential. Remember before we said, maybe it kind of looks like it might be an exponential or logarithmic or something like that. So we'll talk about what happens if we make the wrong assumption. All right, so step number 6 was draw the maximum and minimum gradient lines. So that's what we're going to do right now. So the maximum and minimum gradient lines are just, if I were to draw a line of best fit, remember the error bars are saying that this value could be anywhere in this range. So really it's okay if it's up here somewhere. Okay, this one's okay if it's down there. So what I want to do now is I want to draw what is the maximum possible slope, the maximum possible gradient for a line that will fit my data. Okay, so I'm going to try going through the top of this one right here and then through the bottom of that one. Now I do want to make sure that as I draw that line, it goes through the error bars for all of the others. Okay, if it's really, really close, then it's okay. See this one right here, it looks like maybe it won't go through, but as long as it's really, really, really close, it's probably okay. If it's not really close, then you may need to adjust it a little bit. Okay, so I'm going to go ahead, go through the bottom, and we'll draw in that one up through the top. So that is my maximum possible gradient. And then what I'm going to do is I'm going to draw the minimum possible gradient, which is going to be, well, if it goes through the top of this one and then the bottom of that one. And you'll note, again, it should be able to go through all of the error bars. If it doesn't, then adjust it a little bit. We want it to be able to go through all of the error bars. Okay, so something like this. All right, going through all the lines. Yep, looks pretty good. This one looks like maybe not quite, so I'm just going to go ahead and adjust it just a little bit. Okay, so that I make sure to go through that point. So at this point, I'm going to go ahead and draw in this one. All right, just like that. And so now I have my minimum gradient, right? The red is the steepest it could possibly be and still go through all those error bars. The black is the least steep it could possibly be. Okay, now the last thing that the worksheet wants me to do is to calculate the uncertainty in the gradient. So that's our final step. So we're going to go back to this now. So to find the uncertainty, what we're going to do is we're going to find our maximum slope, we're going to find our minimum slope, and then we're going to average them to find the middle slope or the average slope, and we'll find out how much those slopes deviate from our average. Okay? So here we go. We're going to first find the slope of the red line. So you want to try to pick points that are far apart. Don't pick points that are close, because the closer points are, the more inaccuracy there is in your readings. So this red line looks like it goes through 0, 0 here. And then I'm going to pick another point out here that I'm fairly certain that it goes through, but far away. So this one right here, that looks like 20, 30, 31, comma, 45, 48, 51, 51. Okay, so with those, I should be able to get my slope, knowing that it goes through 0, 0 down here. Oops, knowing that it goes through 0, 0 down here. Then I should be able to get my slope. So the slope of my red line, the maximum slope, or maximum gradient, would be 51 over 31. And I'm going to go ahead and put that into my calculator. And I know I want a decimal approximation, so 1.6. Again, I'm working with 2 digits, so that's equal to 1.6. Okay? Now I'm going to do the minimum, which was my black pen there. So we're going to do the slope minimum, and we'll do exactly the same thing. We'll try to find a point where we feel comfortable with it going through. I'm going to say that it's close enough to this one right here. I'm comfortable with that. So that would be 35, comma, 54. Though this time it doesn't go through 0, 0, but it looks like it goes through 0, comma, 3. Okay, so I'm going to use those two to get a slope. So it'll be 54 minus 3 over 35 minus 0. And now I can get that slope, which will be 51 over 35. And that gives me 1.45 or 1.5. Okay, so the maximum slope is 1.6, the minimum slope is 1.5, and with that, I should be able to finish this. Now, I'm actually going to change these numbers slightly because when I calculated these came from my points here. And I'm fairly certain that these are 31.0 and 51.0. I'm okay with saying that this is 35.0, 54.0. So I'm going to go ahead and I'm going to add in a third decimal place. Okay? So I'm going to change my 1.6 to 1.65 and my 1.5 to 1.46. Okay? And this all depends on how certain you are. So this is, again, saying that I believe that this is 51.0, 31.0, because I'm picking points where it goes right through the grid lines there. Okay? So at this point, I've got two slopes, the maximum slope, the minimum slope. So we're going to find the average slope. The average slope will be right through the middle of those. So I'm going to go 1.65 plus 1.46. And then we'll divide that by 2, and we get 1.55 or 1.56. So M average would be equal to 1.56, keeping consistent with my significant figures. And now that I have my average slope of 1.56, then I can find the uncertainty in the gradient, which is that it can go all the way up to 1.65 or all the way down to 1.46, which is plus or minus 0.1. All right, and that's all there is to it. Why did I say 0.1? Because 0.56 goes up to 0.65, 0.56 goes down to 0.46. That's a difference of 0.1. So the uncertainty is this is what I believe it is, but it could be as high as that, as low as that, so plus or minus 0.1. Now, remember that the point of this is that this is the slope now between y and x squared. Now, if this is really the slope between y and x squared, I should be able to write an equation now. The equation for the relationship that I had here in the beginning should be equal to y equals mx, the slope, so 1.56 with our uncertainty of plus or minus 0.1, times x. But x, remember, was not x, it was x squared. So I have now created a model for my original data based off of this process of linearization. Okay? Does that make sense? Hopefully that's kind of clear. What I want to do right now before I finish the video is show you what would have happened had we used a point that was, sorry, not a point, had we used a model that was incorrect, like say an exponential model. We said maybe it was exponential. So let's go ahead and do that. So exponential model, I'm running out of space, so let's go ahead and just do it up here at the top. So with an exponential model, the x value will now be e to the x power, because we're saying exponential is y equals e to the x, and then some constant in front of it, right? And so that would be the slope if it's y equals, and this becomes my new x. So that should become linear. All right, so e to the x and y. And so I need to do e to the power of each of those. So I need to do e to the power of 1, e to the power of 2, e to the power of 3, and so on and so forth. So we're just going to do those right now. E to the power of 1, e to the power of 2, e to the power of 3, e to the power of 4. I'm going to write those down. So e to the power of x here would be 2.7. That's, yep, 2 sig figs. I got 7.4. I got 20.1. I got 55. Okay, and then I need e to the power of 5 and e to the power of 6. So 148, which would go up to 150, and then 403, which would be 400. Okay, I would have to write it though as 4.0 times 10 to the second, but for our purposes, that's not super significant. Now I put in the y values. So the y values, remember, were 3, 7, 17, 28, 41, 58. Now, when I put these points on my graph, okay, so you've got those on your paper. I'm going to go ahead and put them on my graph now. So if I go to 2.7, 3, so that's somewhere around here, and then 3, that would be my first point. Okay, 7.47, so 5, 6, 7.4, 7 should be somewhere around here. That's looking all right. And then 20.1, 17, so 20, 17, which should be somewhere around here. And then 55, 28. So that's already way off the graph, but you can see that it would be way over here, right? 35, 40, 45, 50, 55. Okay, so 58 would be like way over here, and yet 28 would only be somewhere around here. And so you can already see how this graph, rather than going straight, it's not really going straight, right? If you see my ruler, there's not really a way to draw a straight graph that would go through all those error bars. Besides, if I'm careful with my sketching, you can see that it's curving, okay? Now you may say, well, that's because your points go off the graph. Well, it doesn't really matter. If I would have squished it up, then it would have just been more apparent that these graphs would go steeper, and that as we get farther out, it would smooth out. Okay, so look at the points. It's okay to make a guess. If you don't know the physics behind it, and sometimes you won't, then you may not be able to guess exactly what type of function it is, but use the clues. Assume that if 0, 0 makes sense, assume 0, 0, right? A ball rolling down a ramp. After 0 time, it should have rolled 0 distance, right? So make assumptions, make a good guess, okay? Once you make your good guess, then try it out. That's what we did. The quadratic worked out nicely. We got a fairly nice straight line. We were able to draw a straight line that went through all of the error bars, which means that we probably chose the correct function. And from there, we were able to create a model. We were able to find the uncertainty and the slope of that linearized line. Okay? You can do this for any type of function. Pay attention to what the original graph looks like. Decide what type of function it is, and then linearize it by changing either x or y, though most of you will be more confident with changing x most of the time. All right, that's all I got. Go ahead and try the other 3 problems in this worksheet. Peace out.